Hello everyone, my name is Petri Mustonen and I'm a senior antenna engineer at Radientum. My topic today is to overcome connectivity challenges in IoT tracking devices. I will be mainly focused on GNSS, but I will also talk about Bluetooth and Wi-Fi. So first, a little bit background. So this presentation is based on the case study or design we made to our customer. So the customer had a need for a low cost but high accuracy GNSS tracking device, which should also work with different orientations. The most dual band GNSS devices are currently using patch antennas. However, there's the problem that those antennas can be quite expensive or even large. So our approach was to make all of the antennas with PCB traces. However, it's known that there will be limitations with that kind of approach. For example, the trace antennas, we don't have a right-handed circular polarization, but the polarization is more or less linear. Also, for the dual GNSS usage, there are some requirements like a group delay, maximum group delay, and maximum phase center differences between the bands. So here we have the information of the DUT. At the left picture, we can see the PCB. It has the openings for the GNSS dual band antenna, Bluetooth antenna, and a Wi-Fi antenna, which only works at 2.4 gigahertz. Then at the center, on top of the PCB, we have a battery, and also the device has NFC tag, which is glued to the top of the chassis and connected to the PCB with two pogo pins. And the chassis itself, it's just a plastic rectangular cover. The PCB size is about 80 millimeters by 40 millimeters. So here we can see the antenna specification for the module we were using. It has some requirements like a minimum active antenna gain, 70 dB. It has the right-handed circular polarization, which we don't have. And then there's the phase center variation, which is 10 millimeters at maximum. And then also a group delay variation, a 10 nanosecond max at each GNSS band system bandwidth. And then also there's the inter-signal requirement of 15 nanoseconds. Here we can see the GNSS blockchain. We have a antenna, single feed antenna, and antenna matching. And after that, we are splitting the RF traces to separate the two GNSS bands. We have their own LNAs for both of the bands. And after that, there's again the filtering, and then there's the combining of the traces to the receiver input. Now here we have the first efficiency measurements and simulations for the GNSS antenna. This case is only with the PCB and covers, so not the rest of the mechanics. And from the results, we can see that the antenna efficiency is really good in both simulated and the measurement. But then also we can see that the simulation gives a little bit more optimistic results than the measurements, which is not a surprise. Now what happens then when we add the full mechanics? The dashed curve here now is the simulation with the full mechanics, and then the continuous line is the same as in previous slide, so the PCB case only for reference. So with the full mechanics, we can see that there's some resonances appearing here, which will affect the efficiency of the GNSS bands. So that's something we want to get rid of. And from the simulations, we could see that the reason for this resonance is actually the NFC coil. So then how we can get rid of those? So we tried to implement floating inductors to the NFC coil to the PCB just next to the pogo pins. And the effect of those can be seen here. So it's also simulated values with different floating inductors. The 0 ohm case here is now the same as the previous slide, so no inductor at all. And then we can see that if we start to increase the inductor value to 5.6 nanohenries, the resonances will start to move to the lower frequencies. And then with the 12 and 15 nanohenries, actually both of the bands are okay, but still we can see that the resonances are now here in the middle of the bands. But finally then with the 68 nanohenries, we can actually see that the resonances are gone and the curve is very smooth. So based on these simulations, the 68 nanohenries would be the best case. Now here we have the same thing with the prototype measurement, and the same behavior can be seen here also, but the frequencies don't match with the simulations. For example, now the 0 ohm case, we have the resonance here in the middle of the bands. And then when start to increase the inductance again, we can see that the resonances are moving to the lower frequencies. But then even with the 68 nanohenries, we can see that there is still the resonance here close to the upper L band, which is still affecting the efficiency here. So based on these measurements, now the 0 ohm case is actually the best because it doesn't affect either of the GNSS band. The difference between the simulation and measurements maybe come from the layout. From the simulations, we didn't take into account the traces or the bad capacitance of the traces and the pogo pins. And then also the NFC coil maybe wasn't modeled that accurately. So the inductance maybe was incorrect. So here there's the same results with the Bluetooth and Wi-Fi antennas. We can see at the left there is the Bluetooth, and it's quite heavily affected to that NFC coil. And on the right side is the Wi-Fi, and we can still see it also there, but it's not as big difference as it was in the Bluetooth. From the results, we can actually see that the 0 ohm case here would be, again, the best, but the 68 nanohenries, it's still pretty okay. And for the Wi-Fi, it's the same case. Okay, and then there is the measurement result for the Wi-Fi and Bluetooth antenna. So it was measured with the 0 ohm because for the GNSS we saw that the 0 ohm was best there. So we measured the Bluetooth and Wi-Fi antennas with the prototype first, also with the 0 ohm. And we can see from the results that actually there isn't any problem here. The efficiency is still quite good, and there isn't any drops for the efficiency. So in this case, it seems actually that the 0 ohm would be best then for all of the antennas. Here we can then see the group delay measurements for the RF front end, and in the table there is the minimum maximum values taken from the graphs, and I calculated the maximum in-band difference values here, and the maximum is 7.4, and it's still within the specification, which was max 10 nanoseconds. And also there was that maximum interband group delay difference. The specification was max 15 nanoseconds, and from the measurements we can see that the measured value maximum was actually 22. So based on this, we are still in the specification. Here we have the RF path gain measurement. These gains don't have the maximum antenna gains included, which are shown here. But even if we include these gains here, we can see that actually we don't meet that requirement of 17 dBs of minimum active antenna gain, at least for not the lower L band. For the upper L band, we are actually quite close to that limit. Then here is the antenna phase center simulations results. It was simulated from 4 different propagation directions and 2 different frequencies. And at the table, there's now the phase center coordinates, and the phase center difference was just calculated from these coordinates. And from the results, we can see that there is the 7.4 millimeter is the maximum one. and at the specification, the requirement was less than 10 millimeters. So based on the simulations, we are still within the requirements. This was maybe one of the most important things when designing the antenna itself, that we have to make sure that we actually meet this requirement. Then the last slide, summary and conclusions. So a dual band GNSS device with Bluetooth and Wi-Fi was designed, and the antenna measurement shows a good performance with all of the antennas. And the NFC was causing problems within the simulations, and because of that, we implemented the NFC floating coils. But then with the actual prototype measurement, we noticed that they weren't required after all. So that 0 ohm was used then. And for the group delay measurements, we saw that we are within the specification, and also the antenna phase center case, which was done with simulations. But then there was the active antenna gain, where we actually didn't meet that 17 dB limit. But then the device was ready and it was manufactured. And after that, the customer did some field testing together with the U-blocks, and their test showed that the device was working correctly in that high accuracy mode and was using both of the bands correctly. So the design was successful. Unfortunately, I don't have any data to share here for those measurements. So that was everything I had to say. So thank you very much for watching. And then it's time for the questions.